That's pretty cool. Let me just quickly check one thing. Cool, I muted it. It seems to work. So at least I don't have the headset warming up my head all the time, and I can just hear myself better. Yup. Let's get going, because we were doing, and I should probably have to check that, because I should probably make sure that I have the microphone in an optimal position, so you can just, because I have the setup, it's a Yeti, and I have it like so it kind of catches the sound from the front. Yeah, that should be, here should be okay. And so we were still with problem one. I kind of feel like I have to get like, you know, a bit used to all this stuff. Sort of the process of getting a bit more into the details, right? And we did like A, B, and C as well. We did, but we didn't get to the like. So we did. I did C, but I didn't really develop that mathematically. So it gets there. I'll try to do that, but today I'm feeling a bit more like we should try to understand what maybe do, you know, there's this thing called the probability current that I have to dig into, and I should probably do that because it's asking me. So if we start with the same initial wave function, do eigenfunctions are real and isotropic, whatever that means, right? But I'm assuming that's going to be something that, you know, it's useful to learn because it might pop up in future exercises. Take the two partially overlapping regions omega 1, omega 2 to be two concentric spheres. Okay, so now we've got two concentric spheres. Compute the probability current that flows through omega 1. Okay, and omega 1 is the one that's outside because the radii of omega 1 R1 is bigger than R2. So let's maybe open up Paint. And so we need to do something, we need to calculate something that's called the probability current, which it just by the word, like, so this is going to be something like we've got like a region here and a region here, right? And so this is R2, no, omega 2, and this is like omega 1. And so like let's think about this for a second, right? So we have a wave function, right? We have a wave function, maybe something like that. Oh, baby's up. Give me a second. Be back in a second. We're back. Are we back? Yes, we're back. That works well. Like it. Yeah, cool. Ugh, playing with the light, but anyway. So maybe it'd be better. So exactly. So what I was trying to think about is like, so we have the probability. No, we have the wave function that in a really simplistic two-dimensional way, you know, it could be something like this, right? In a way that like it has positive and negative regions. No, I mean, it is actually, I don't know if that's something you could, yeah, actually can do it like that, right? It's just complex, and you can represent that with a complex number, I guess, right? Yeah, each of these points being a complex number. So then you have like the probability distribution, no, sort of the probability density function or something. That would be, you know, the square root of these kind of stuff. And I like, so, you know, that would kind of have a shape, right? Like this is probably wrong, but like, of course it's going to be only positive, right? And essentially like whatever, it's going to be something like that. And essentially if you, I guess, integrate over these, and that's what it means that it's normalized. If you integrate over these, and I'm definitely going to be wrong with notation. I'm just like, I've got close to zero math skills, and so don't get mad at me. I'm learning on the go. I guess if that's a function of x, you would say something like that. I have no idea, right? But if you integrate over these, then you should have a 1. I think that's what it means, that the probability should add up to 1, right? But then there's this flux thing, right? Which like, I guess if we have, like, let's imagine that this is we're going to plot the two probability distribution functions. That is like x, right? And let's imagine that we have two regions of space, right? So this is 1, this is 1. So this would be omega 2, and sort of these would be omega 1, right? The wider one. So these are sort of the diameters. Like, it's just like if you look at it from cross section, like if you do a section, like if you cut and look at it from here, right? Now here comes in the question, what does it mean for the two eigenfunctions to be real and isotropic? So real means they're not complex. Isotropic, I don't remember, because this is gonna, I guess, you know, the exercise always gives you information that helps you you know, find the solution, right? Like in a way, like we can make certain assumptions because of these, but I just don't know which assumptions. An isotropic function. So what is an isotropic function? I just hate Quora. I don't want Quora. It's the user experience is awful. I just like Wikipedia way more, but oh god, like so isotropy is a uniformity in all orientations. It is derived from the Greek isos, and tropos, way, equal way, precision dependent subject area, of course. Physics. Boo. Material science, microfabrication, antenna radio, computer science. We say a volume such as a computed tomography has isotropic voxel spacing when the space between any two adjacent voxels is the same along each axis. Okay, so it just says they are isotropic. It means they have the same shape, right? I'd assume that's what it means. Isotropic wave function. Especially isotropic. Okay, so let's go. Let's check what they say here. given function is spatially isotropic. So is the transformed wave function in k-space what the hell? Isotropic. Therefore, the integration is described as follows. Okay, so the isotropy is telling us something about how can you integrate something, right? Spatially isotropic. God. Isotropic harmonic oscillator. Let's see. The Hamiltonian of the isotropic harmonic is the following. Yeah, I don't know. It's complicated, man, because it's definitely going to make probably the integration easier, right? But I just don't know exactly how. I don't want to take a look at the solution. So, but again, let's go back to. So I guess, you know, the fact that they're isotropic, it probably means that maybe they just have the same shape. So I don't know. So it could just be something like these. Let's imagine, right? So you have these, and then you kind of have these, or something like that, right? Yeah. Which maybe means that maybe one of the things, maybe what this means is that the integration, so the area, right, is just they're just proportional, right? So like if the integration of this one here, right? So if you do something like these and you integrate that, and it's say like this is, you know, whatever, like let's say y, right? Then the same thing for psi y, psi 1. Kind of it's like probably like times whatever k, like a constant or something, right? Because they're isotropic, this means maybe, I don't know, because I don't know if it's a property of the cap of it's sort of a relative property to the wave functions, or it's just that they are each spatially isotropic. This means that they are maybe just the same everywhere, so they are literally like, you know, like this. So they are just easy to integrate, right? You know what I mean? Like you don't have to do anything complicated. It's just an area of it's just a simple area calculation. Maybe that's what it means, that they are isotropic, so that they are across space, that the probability is the same, right? Maybe that's what it means. So these are two candidates of what this isotropic thing means here. They're real and isotropic. Take the two partially overlapping regions. The fact that they're real, it also means that they're conjugate is the same, like the non-conjugate. Like so that, you know, that the you know, that psi 1 star equals psi star. That's what psi 1, like that's what it means for this to be real, right? Because the complex conjugate of a real is the same real, because it just doesn't have a complex part anyway. So this is what these things mean. But now let's try to understand the probability current that flows through omega 1, through the region omega 1. So this is what's complicated. So because the definitions I found were quite mathy. In quantum mechanics, the probability current, sometimes called probability flux, is a mathematical quantity describing the flow of probability. Specifically, if one thinks of probability as a heterogeneous fluid, then the probability current is the rate of flow of this fluid. It is a real vector. That changes with space and time. The probability currents are analogous to mass currents in hydrodynamics and electric currents in electromagnetism, as in those fields the probability current is related to the probability density function via a continuity equation, transport equation. The probability current equation is an equation that describes the transport of some quantity. It is a particularly simple and powerful when applied to conserved quantity. The probability current is invariant under gauge transformation. Okay, that is just way this whole gauge theory and stuff, that's still something that is far away from the concept of probability current. Is also used to is outside of quantum mechanics. The change over time. Okay, I guess this is some kind of rate of change. Again, it's like maybe a derivative of something, right? So it's like how, because what they're saying is it's also used when you deal with probability density functions that change over time. And so you kind of, I imagine you have your wave function and time 0 your probability density function wave at time 0, the probability density function at time 1, and you want to calculate how much is this changing through time, right? Which I guess, I don't know what does this tell you though about the specifics of the problem, right? It's how does the probability change from one region to another? I don't know what does it tell you from a utility perspective, but I think I can see what it is, right? So it's telling you as we move from this region to this region, right? There's the probability density changes in a way, right? So I guess this is going to be somehow something. Let's assume, to me, what makes the most sense is that like things look like a rectangular thing, right? So that things look like these. So we have our thing here, and so in omega 2 the probability function is isotropic spatially, so something like that, the density function, and in omega 1 is maybe something like these, right? And because they're inside the other, these flux is probably going to be something like, so the flux is going to be something like these are the regions. So I don't know if it's not just something like it's the flux is kind of 0 here, right? Because it's not changing. But then when you get here, it just goes up, and then it goes down again, right? So it's going to be what this means is that if you consider the probability density probably of the combined system, there's a change in probability density distribution here. I guess that's what it means, because you can aggregate them. It's a particle and two normalized energy eigenfunctions. Corresponding to the eigenvalues. Assume that particles in region 1. So yeah, exactly. So those are two separate regions. They have two separate probability density functions. Blah 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 blah. But if they are concentric, then there's going to be higher chances of the particle being found in that omega 2, right? And that's what the flux is telling you, is that it's how the probability density function changes. But how do you calculate that? I have no idea. So free spin 0 particle. In non-relativistic quantum mechanics, the probability current J of the wave function psi of a particle of mass m in one dimension is defined as, oh god, the wave function. So basically what this is saying is, so this is just a given definition, and it's like, let's try to understand that, right? It's well, first of all, how is that supposed to be a vector? Is it because kinetic momentum operator is the position basis? Spin 0 particle, spin s particle. I mean, these things change a lot. Connection with classical mechanics. First of all, what is a spin 0 particle? Again, I guess at spin 0 particle. I don't want German. I hate Quora, but like, so these are different types of particles, and they have the probability current. But it's interesting, right? Because this has got to do with you know, the energy stuff, right? Or the momentum, I think, whatever. And then it's like the complex conjugate times, which we know it's real, so we know it's the same, right? Okay, so it's that thing squared. No. Oh. Ah, interesting. I mean, if this is what we would pick, right? Like, that's the same like these. Because we know that psi, like, they're real, right? So psi star, like, this is equal to these. So this whole term goes to 0. So is the probability current 0? That wouldn't make sense, though. I mean, I don't know. Let's check. Maybe, I mean, if that would be a spin 0 particle, that seems to me like, because psi star equals psi, right? So I'd say this term equals this term. So this term minus this term is obviously 0, and so 0 times this is 0, and so this is 0. That would be probably too easy, but and we can try to think about why is that. In the case, let's see, D. Okay, that's definitely not this. The current density is easily computed to be okay, and vanishes at R1 since one of the or the other eigenfunction vanishes at that point. This can be seen through the continuity equation in the following alternative way. The current density is computed to be okay, so this is definitely one of these. No, what? There's a sinus. Okay, so it's not a spin 0 particle. It's just something. Why? How do I even know that? Now it was 3 current. So what is the function? Isotropic oscillator. I guess yeah, the thing is, I went ahead of myself by just expecting that to be, so I just didn't know where that formula is coming from. That's obviously non-zero, right? I mean, again, that should cancel out though. Vanishes at R1 since one of the other eigenfunction vanishes at that point. Yeah. So I mean that's in a way, if I understand that well, it means I was not wrong. This means this vanishes in R1. So this is 0 in these regions, because one of them is gone, right? I'm happy that at least I was not that wrong. I just didn't know where that is coming from, this one specifically. The current density, and how do I know that is this specific function, the one that is used? This can be seen through the continuity equation in the following alternative way. And whatever that means, continuity equation. The last integral vanishes because of the orthogonality of the eigenfunctions. Well, it's complicated, but okay. I have this problem that I'm just lazy with the math part, and maybe I should just kind of solo the peel the hard way, and then have because I'm almost like I should go and do these, right? Like, because I made the calculation in the last stream, but I just never really calculated that it gets to these expression, and then it's of course easy when you look at the solution to say, ah, yeah, that's what I meant. It'll get better. I promise it'll get better. I'm curious to know where and how could I just found out that this is the thing, the current density formula. Why isn't it like probability current? Maybe I'm looking at the wrong thing. The current density. No, this is a probability current, right? Flows through, yeah. Compute. Okay, so spin 0 means the particle has spherical symmetry. It means it looks the same by all axes. Spin defines the angle through which the particle returns to its original waveform. The equation is given by angle blah, 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 blah. Spin 1, spin 2. Okay, so this is about like symmetry or whatever, I don't know. Probability current density. Probability current. Motivation examples. Maybe examples. Oh, look at these. Particle in the box. Yeah, that's probably... No, that's the same thing, man. Well, because it's not in the box in this case, right? A plane wave. I wish the solutions would explain a bit more the reasoning behind why is it this way. R hat h bar divided by 2 times m. Like, that is awfully similar to these, but then oh, I know. I think I might know. Yeah, look at these. I think the reason this is this way, maybe, and I'd have to develop that, right? But it's the same. It's maybe got to do with the fact that if you take the particle in the box model, you have these, right? And this L like being the R, so that they're probably the radius. And so the thing is the following, because they're isotropic, and what it means in this case, because they're isotropic, this means what's isotropic is the wave function, not the probability density. Crap, whatever. That's although you can derive one thing from the other probably, but what it probably means is that of course these derivatives are what, like 1? No, like you know, I think that's it must be derived from here. It must be derived from the fact that, like, or maybe just a plane wave, and we take that stuff, which would, you know, you can turn into a sinus equation, right? Because of, you know, these, and then you get this K and R and stuff like that. So I think you just take that stuff, and then you know what I mean, right? So I'm here being lazy, knowing that I should do that, and I just don't want to do that, but like, maybe let's try. I don't know. So you have the A, and then you have e to the power of I, and this is super laggy, KR minus WT. Right, and then I think this e to the power of I. There's a trigonometrical representation of these. Which I should just memorize. It's cosine plus I sine, exactly. Cosine of x plus I sine of x. Right? So it'll be like cosine of like kr minus wt plus I times sine of k times r minus wt. So that will be, you know, something like these, right? Now, yeah. But now again, this is the so this is, I'd say, a generic expression for, like, you know, the psi 1, say, right, and or psi whatever. So psi 1, psi 2, whatever it is. Now, because we have this formula, right? So this is basically that. Now the derivative of that, so this is, you know, times its derivative, right? Let's just compute one of these, because the derivative of sine cosine is, you know, is the minus, right? I think the sine cosine derivatives I think it's like what, the sine is cosine and the cosine is minus sinus, sin, cosine. So you would kind of say, you know, it's like these, so the derivative of these, right, would be minus of krwt plus I cosine. It just is all, there's a lot of lag, but whatever. I don't know if that's gonna pop up. Yeah. And so now we're doing times that. So it's like, you know, these times these, and these times these, like cosine squared, because you know, I think, and then again, I think sine squared. I think there's again another equivalent, like can make a or sine times cosine. There's something you can do there. Believe me, I'll just try to get there. Formsammlung. I don't want German, but we'll just probably can translate in there. But I think it's going somewhere. I think that is I want English, man. Nothing against Germans though. I like German, but it just makes mathematics complicated if you have to understand things differently. You know what I mean, right? So I'm kind of like, I'm trying to get there to the fact that I just don't know. Yes and no, right? Because actually, maybe I'm not. That's not the right path, because this is definitely the derivative. Maybe you can wrap it up somehow. I don't know. WT. Sine. There's no like some kind of equivalence of like sinus times cosine and stuff like that. I thought there was something, probably, but not. Okay, so yeah, look at this. So sinus times cosinus times twice, right? Is the twice that. So sinus times cosinus is like sinus. It's 2 times the angle. You know, maybe that's where There's something you can do here. That's why maybe the two, because sine of x. Can I do something like that? Does Google know? Is Google smart enough to actually plot it? Oh, that's cool. And that's just a sine wave, isn't it? And that's just a sine wave. It's 0 here, and it's 1 here. Like it's... Yeah, okay, it's twice the angle, or it's like this, yeah, 0 here. It's not, no, it's not sine. Okay, it's definitely smaller. Yeah. But it reaches the max like more or less at 0.78, right? Okay, that's different. Yeah, it's not the same. It's not exactly the same. Cool. That equivalence is true though. So yeah, but I could always just add a 2 and then do that, right? But this is literally saying the derivative, so that's not the right approach. That's definitely not the right approach though, because in the formula they keep the derivatives and stuff, so they actually don't do what I'm just doing, I think. It's like I don't know where they take that function from, that equation from. It's like definitely awfully similar to these, right? But where is the sinus coming from? It's because it's the derivative of psi 2 times psi 1. I guess that's the same, because I guess this is just the calculation. I guess this is just the formula for the calculation of, you know, it's like it's the probability current for a one single wave function, and we're looking into 2 separate wave functions, so maybe that's different. So probability two wave functions. Probability current and current operators in quantum mechanics. So what does it do these? Does it take me anywhere interesting? It's not loading or what? Come on. Oh god. But it seems like it's standard in like it's definitely something standard in the quantum mechanics stuff, which I've never seen before. Probability current, page 5. There you go. So let's take it so again, it's just one wave function, right? And so using the explicit expression from the Hamiltonian wave, it addresses the potential cancel. So it does use these, right? But I don't see this sinus anywhere. the charge density, we have therefore a probability current. Well, okay, actually, maybe this makes sense. If this is the formula, to use, it makes sense, right? Because the imaginary part. No, it doesn't make sense either. Because I was thinking the imaginary part, if you take that wave function, then that's how you get a sinus. But then it just maybe if I would develop it this way, you know. This is something to do, like if I would just develop that, like maybe it does indeed, like if I develop that, I can just again then pack it again into like, okay, that is wave function, right? Maybe I should just do that, but I won't do it today. I won't do it today. I think it's definitely how much time I have left actually, but I get the concept, just so you know a formula to calculate the probability current. But I think if I develop that and I just multiply these things, you know, I'd get like the so I get like minus cosine. Let's just call this x whatever, right? Sine, because it's the same everywhere, times, okay, times sine of x, and then I times cosine square of x, and then we'll get minus I times the sine squared of x, and then plus, okay, I times I is like -1, so minus sine of x times cosine of x. And so actually this is then this whole thing squared, right? So this is plus, so it's like basically, so this is basically sine times cosine, like sine of x times cosine of x squared, and I think this is just squared, right? I think you can do that. I think, I don't know. And then minus, and then you have I of minus I times cosine squared of x plus sine squared of x. This is something, right? Isn't it like, isn't that like a trigonometry identity as well? Like the cosine squared plus the sine squared is equal to something. Well, if it's just the imaginary part, then we can get rid of these. If that's the formula, right? If the formula is the, what was that? Where is that? Was it here? No. Here. If that's a formula, we just keep the I've just done that, so we just keep the imaginary part. But again, that's with the function and, you know, in itself, right? That's the problem. Here is like we've got two functions, two wave functions, but we can treat it as one actually. So we just take the imaginary part, and then it's just cosine squared and plus sine squared of x. So I don't know. Yeah, that's one. Yeah, I knew, like, okay, that is actually one. Interesting. So I don't know where that takes me, to be honest, because that's one. That's one, but that doesn't help me at all, right? Because that leaves me with that doesn't, it definitely doesn't lead to these, right? It definitely doesn't lead to these. There's something, I'm missing something with the, you know, how to calculate that for two-way functions. As we all know, the probability current density is quantum mechanics is defined like these. So it's self-transposed times this. I mean, that's the, for simplicity, let's work in one dimension, and let's suppose that the wave function is a times cosines kx. Cosines kx. So then, and what is this equation of continuity? Yeah, j equals 0, exactly. That is interesting, right? Like, what I'd like to understand what sort of the meaning of that way of expressing things mathematically, to be honest. But how do we get from here? How do we get this sinus out? That's what's confusing me, because this is this, right? So this is what you're just saying is like psi2, the derivative of psi2 times psi1, and derivative of psi1 times psi2, that actually matches this definition. It also doesn't, but it's super similar. But I don't know where the sinus is coming from. That's the problem. Is it maybe somewhere in just the starting with the same initial wave function, assuming that two eigenfunctions are real and isotropic, take the two partially overlapping regions. Oh no, yeah, okay, concentric series, nothing. That's kind of what I'm missing here. It's like, where is the sinus coming from? This I don't know. Because you can assume something like these, right? No. Yeah, of course. Oh God, like I keep getting confused, because psi1 is not the wave function. Psi1x is just an eigenfunction, whatever. Like, that's not the wave function. The wave function is that. And so you need to, like, the wave function of x and t, right? It's like you actually have, you add that evolution component there, because that's like what adds a dynamism to it. Like, it's this eigenfunction times the evolution, and that is, and yeah, and that is where you take the sinus from, of course. I keep making the mistake that psi2 and psi1 are actually wave functions, and they are not. They're not wave functions. They are these whatever eigenfunctions, energy eigenfunctions. These are just the functions that describe how the energy behaves, but that's not the wave function. The wave function is how is actually that evolving, right? That is my mistake, and I think I can make that derivation next time. I'll give it a try. Yeah. That is my mistake, because then it makes sense. Then it makes sense. You get this kind of stuff because you do the derivative and all this blah blah blah, and then you know, these things are part of the expression. Like, if that's my starting point, right? The derivative of this is kind of the same thing times this, right? But then that's like a sinus whatever, and then you get these things, these factors inside the argument of the sinus function, and that makes sense. I think that's how. That was my mistake. It's just the fact that why, and that's just confusing, that they just used psi1 as the way to label the eigenfunction, when that is not necessarily the wave function. The wave function is something that is a function of that, right? That is what's confusing me. But I think I got it. Cool. That was a good session. Productive overall. I think I got problem 1 almost solved in like, what, 4 hours? I just have to work out through the mathematical stuff, make sure that the things make sense in here, and then we'll just jump to problem 1.2. And we have 344 pages ahead of us. Sounds good. Goodbye.